Welcome to the video ferritic-pearlitic grades. In the previous video talking about ferritic grades, we have seen how it are gaining popularity the high silicon ferritic grades. So with a 3.5 or 4.3 silicon, substituting ferritic-pearlitic grades. But why these grades are becoming so popular? It is not because of the poor casting process of a ferritic-pearlitic grade, but because of a poor definition of their ductility. So we have a misunderstanding in the conventional standards. And this misunderstanding is that ferritic-pearlitic grade, having a large scatter in hardness that is driven by the casting wall thickness, have properties that define the minimum strength based on the minimum hardness and the minimum elongation based on the highest hardness. And this is describing a poor ductile material. And so for this, these high silicon grades having the same yield appears as attractive because they seem to fulfill the same properties requirement and the ferritic-pearlitic, and at the same time they have surely a much more controlled hardness. But since the 70s, the Fiat approach defined hardness controlled grades of a ferritic-pearlitic grades applicable on uniform casting, as is typical in the automotive industry. And this approach is being followed by a major automotive casting producers, as is Georg Fischer with the C-Baudur trade name. So in this slide, you see these commercial grades defined by Fiat and Georg Fischer. And also Georg Fischer is proposing these grades with the suggestion of bionic design, so designing casting in uniform wall thickness. That is a pre-requirement to achieve uniform hardness in ferritic-pearlitic grades. So in 2001, we proposed to the ISO and EN working groups of material standards the adoption of the material quality index for definition of ferritic-pearlitic grades. So separating the Brinell Hardness range from the material quality. And this approach is much more efficient for the designer in controlling the critical strain versus triaxiality factor and the strength ratio between the ultimate tensile strength and yield strength. More recently, in the last 10 years ago, Zanardi Fonderie patented a new material that is called IDI, isothermal ductile ion, that is obtained by treatment a nescast ferritic grade with no alloying, then with no segregation, with uniform properties in different wall thicknesses from 25 up to more than 75 millimeters. This is obtained by a special structure that is ferrite and pearlite, called in an interconnected shape, called ferritic structure, and able to grant 800 megapascal ultimate tensile strength, 480 yield strength, and 6% elongation in all these wall thicknesses. This is because the pearlite is obtained by a pearlitic transformation that happens in minutes instead than in hours as cooling into the mold. Here you see the comparison of the mechanical properties. So you see in order the ultimate tensile strength, the yield strength, the elongation, and the fatigue strength. You see how, especially for the elongation, the difference between IDI and a ferritic-pearlitic gray of a similar strength is very, very more significant, much more performant. And so this IDI material should be recommended for engineering design of castings with different and large casting size and significant strength and ductility. This is evident if you compare the unnotched Charpy impact energy that you can achieve on the different grades. The black dots are representing ferritic grades, and here we see the high silicon ferritic grade for this level of strength. The red dots represent the ferritic-pearlitic as cast grades, while the violet dots on the top represent the IDI properties, Charpy impact energy, where you see that the round dots, violet dots, are obtained with the low silicon IDI, while the triangles are representing the normal 2.5, 2.6 silicon grades. So the best we can get with the Charpy impact energy, we get with the low silicon IDI grade. And you see how this property is conserved at 25, 50, and 75 millimeter wall thickness at room temperature. When the test temperature is minus 20 Celsius, the IDI, particularly IDI with the low silicon, is maintaining his better performing in comparison to high silicon ferritic and S-cast ferritic-pearlitic grades. On the three wall thicknesses 25, 50, and 75. And this is even more evident when the testing temperature is minus 40 Celsius.